Hi everyone. Hi everyone. Can you hear me? Okay. So I assume that you can see me and hear me, but I think you cannot see the iPad screen yet. You cannot see the iPad screen? Okay, you can't see the iPad screen. So wait a minute. Let me share the iPad screen and then let us begin our session today. Is the iPad screen also visible? Now, I've done some rough work over there. Okay. iPads also visible or not visible? Not visible. Just give me 1 minute. Just give me 1 minute. Wait. I understand. The iPad screen should be visible now. I think it is visible now. All right. So how is everyone? Before I start the session, I hope all of you are fine. We are in second lecture of NSET bootcamp. This is maths one actually. Maybe you are asking about learnability one. I think you are asking about learnability one bootcamp. This is maths one. Maths one. The first session on maths part of NSET. Okay. All right. So I do not know much else, but I can help you prepare with this. So let us just focus on this part. I would keep on reading the chat and I would begin with a few questions. So NSET I think has 4 sections. One is English, second is logical reasoning, then it is maths, and finally it is learnability. So I took a session on learnability, I think on Friday. English has been removed. All right, no problems. I was not aware. Okay. So we had this section on learnability on Friday. What was the website that you shared in the last class? This is the website that I shared. pepcoding.com. In this you go to free resources. In that you go to level 1. In that I shared a few lectures. Okay. Now let us come back to today's lecture. So we had one lecture on learnability. There I discussed what? I discussed number theory. A few questions on number theory. No, not number theory basically. Arithmetic. Number system basically. Number system. Alright. Number system. I did not discuss any recursion, any DP or any graphs. But we still have one more session on learnability. So in that session, I would do recursion, DP and graphs. Also for today, the questions that I have chosen to teach you maths are the kind that would also touch somewhat on learnability. Not recursion basically, slightly from DP part. Because DP and permutation combinations has a lot of overlap. So the questions of permutation combination that I have chosen will also overlap with the DP information. Alright. Is everything clear so far? So we would be helping you prepare on maths and the learnability part. We already had one session on learnability in which I covered number system, but still there are 3 topics pending: recursion, DP and graphs. But I think you had an idea about learnability, that you would be taught something and you would be required to solve something on the basis of that. Okay. Revant, I'm just beginning. So just connecting the dots with the last lecture, nothing else. Okay. All right. So today we will be focusing on maths. So in maths, the topics that have been selected to test you guys on are, stay with me for 1 minute. One is number theory. So here I would strongly prescribe you to learn modular arithmetic. Modular arithmetic is arithmetic of remainders. For example, if there is a number A and there is a number B, then A modulus B represents the remainder of division of A by B. For example, if I was dividing 47 modulo 3, that would be 2. Okay. So I would strongly recommend to everyone to at least know the basics of modular arithmetic. Why am I stressing too much on that is because most of the people who prepare for like IIT JEE, generally I don't think IIT JEE syllabus focuses on modular arithmetic. So in my times at least it did not used to. I'm not sure about today how JEE preparation is happening these days. I'm not sure, but in my times in 2005, modular arithmetic was not a part of the syllabus. Okay, but if number theory is being evaluated, modular arithmetic is a very important topic. Okay, so at the very least know the basics of modular arithmetic, which means you should at least know these formulas. A plus B modulus C is actually equal to A modulus C plus B modulus C. So I will not go in the details of this. The only word that I am saying about this is that practice modular arithmetic. That is going to be very important. Okay. One resource that I can recommend is brilliant.org for practicing modular arithmetic. I used brilliant.org 3 years ago. I wanted to revise some stuff on modular arithmetic. I used it 3 years ago. It was amazing. Brilliant.org was amazing. Okay. So first things first, number theory, revise modular arithmetic. All right. Second topic where I may not be very useful to you. You might be knowing already more than me. In fact, on the most maths part, you people would be smarter than me. But nevertheless, I would let you know the topics. So exponentials and logarithm. So here, why log is important? Let me tell you the logic why log is important for us is, I hope everyone knows that log is the inverse of powers. I think you are already aware if a raised per x is equal to b, so x is equal to log of b to the base a. I hope you guys are aware of this. 2 raised per 5 is 32 and log of 32 to the base 2 is 5. I hope I have written it correctly. Yes. So 5 is equal to log of 32 to the base 2. So and a lot of our computer science logic is all about binaries. So we have to quickly get back to logarithms. So whenever you would be doing any practice on exponentials and logarithms, pay a close look at binary number system. So most of the questions that you would get would be related to binary number system and how log can involve that. All right. So this is about the second topic. This is my neutral advice. I am not the one who has set the exam, but I am trying to. So see my perspective, how my perspective can be important to you. I am trying to reverse engineer the person who would have set the exam. What would have he thought about? So that person who has set the exam is not a JEE preparator. He is not a JEE professor. He is a guy who is teaching people computer science programming, but he must have appeared in JEE many years back. So the maths question that he would now be giving to you would be coming from a programming perspective. So number theory is going to be important for you. In that, modular arithmetic is going to be important because, for example, I would give examples. No worries. So I have picked 6 questions for today, and in those 6 questions, I would give you an example. Don't worry. So I have a logarithm example ready. All right. Website name is Pepcoding. There are many websites. Geeks for Geeks is the best website, frankly. Why I mentioned Pepcoding is because I am Pepcoding's founder. So I wrote that website. So that is why I recommended that. So the questions over there have been prepared by me. That is why I recommended it. But I think the best website would be Geeks for Geeks. All right. Brilliant.org is for math stuff. Yes. For math stuff, brilliant.org is the website that I am recommending. Some of it is free, some of it is paid. All right. Moving forward. So 2 topics now you know. Number theory, exponential and logarithms, where binary number system is going to be important for you. The next topic is probability and statistics. So I think this would largely be coming from JEE portion only. So more or less like 10th, 12th probability, not JEE, 10th, 12th probability. Nothing too deep there. Permutation and combination. For that, I would have a specific recommendation because permutation and combinations also come in programming in the topic called dynamic programming. Okay. So I would recommend go to Pepcoding. Free resources. Level 1. DP. And just you don't have to code the questions. Of course, you do not know programming. So if you do, good for you. But if you do not know the programming, you don't have to code the programming. Just listen to the discussions. So before I start coding over there, I do some discussion which any lay person who has never coded ever can understand that discussion. I've done that discussion. So at least watch the discussion of 20 questions over there. So this part would help you conquer the permutation combination part of the maths section. Okay. Fifth is ratio and proportion. For ratio and proportion, I have no advice, only that you need to be familiar with the ratio and proportion that you have already done in 10th and 12th, so that much is enough. And same goes for sets, Venn diagrams, that union and intersections, and A minus B, you must be clear with the basic rules. So I have specific recommendation where for permutation and combination, for exponentials and logarithm, and for number theory. For number theory, remember you have to do modular arithmetic. For exponential logarithms, pay a deep look at binary number system. And for permutation and combinations, I would recommend do a few questions. Just watch the discussion on the dynamic programming questions, because that has an overlap with permutation and combinations. And that, I think, would be the perspective of the person who would have set the exam. He is coming from the computer science world, programming world. He's coming from a mathematical background. So I think he would have done an overlap for permutation and combination with dynamic programming. That is what I think. Okay. People can't join. Ananya, for permutation and combination, what I am recommending is this website called pepcoding.com. Okay, don't worry, Ananya, don't worry about permutation and combination. There's one more learnability session. So that learnability session I will dedicate to dynamic programming plus permutation combination. So don't worry about permutation and combination. Ananya, is that fine? That you don't have to worry about permutation combination, because I will take one more session on learnability. In that session, I would tackle this part on permutation and combination, also share the resource that would help you. Okay. Revant, all I said about coding was the person who has set this exam is coming from a computer science background. He's a coder and he also has some maths background. So the maths question that you would generally see would be aligned to computer science programming. So that is what I was saying, that if permutation and combination questions would come, they might have an overlap with a topic in programming called dynamic programming. So the questions to you would look like their permutation and combination question, which they would be, but they would also be dynamic programming questions, which we do in computer science programming. Website name of coding is pepcoding.com. Pepcoding.com. P-E-P. Peppy. Pep. Happy. P-E-P-C-O-D-I-N-G.com. There is a section called free resources. Inside that there is a section called level 1. Inside that there is a chapter called dynamic programming, where there are around 30 questions. You can watch them. Okay. All right. So let's begin. I have 6 questions for today that I will be teaching you. So let me take you through those 6 questions. So the first question is, I call it Benjamin bulbs. This question is basically on number theory. Okay. In modular arithmetic, do we need deep understanding? The basic formulas, the basic 4 formulas. These 4 formulas you need to know. A plus B modulus C is A modulus C plus B modulus C. This kind of 4 basic formulas you need to know. Okay. Sakshi, I can send the notes. So in today's lecture, I will attach the notes of today, also of the previous lecture. Don't worry. Many people can't join the class. So I can raise the point to the team, support team. I don't know why people can't join the class. This is the same link actually. Let me raise the issue to the team. So I've raised the issue. Okay. Ananya, specific sources for number theory, I can point out a article for this on Hacker Earth. Just wait 1 minute. Hacker Earth, number theory. So the least that I would want from you guys is, let me pin this link also. For number theory, revise this, read this link. At least know this link, whatever is that in there, this link. Okay. Revant, I attached, so after the lecture, I get a screen where I attach the notes. So I will attach it there and I will ask the support team to let you know how to access those notes. Okay. All right. Let us come back to today's lecture, because we are getting scattered everywhere. I want to focus on today's lecture now. For recordings, I would raise your concern to the support team and the support team would come back to you. So I am not the person who would take care of that. I am the person who would teach you this class. So let's focus on Benjamin bulbs. That's the first question. Try to get the gist of the question. This is from number theory. and see how it is a programming question as well as a maths question. See, so let us say there are 100 bulbs in front of you. 100 bulbs in front of you. 100 bulbs, electric bulbs. Okay. And electricity, the voltage fluctuates. Voltage fluctuation happens. Fluctuation happens. There are 100 bulbs, a voltage fluctuation happens. So what happens is, for the first time, when the voltage fluctuated, all the bulbs toggled. Toggle means they switched off. So initially 100 bulbs were on. Initially they are all on. 100 bulbs and all of them are on initially. All are initially on. Voltage fluctuation happens, and when the first fluctuation happened, all of them toggled. For the first fluctuation, all of them became what? Off. Voltage again fluctuated for the second time. For the first time voltage fluctuated, all of them became off. When it toggled, when the voltage fluctuated for the second time, half of them turned on. Half of them again toggled. Which half? 2, 4, 6, 8, 9, 10, 12, all the even bulbs again toggled and turned on. Even bulbs toggled again. Now the voltage fluctuated for the third time. All bulbs who are a multiple of 3, listen carefully, all bulbs who are a multiple of 3 toggled again. Multiples of 3 toggled again. Toggle means if they were off, they turned on. If they were on, they turned off. Multiples of 3 toggled. Voltage fluctuated for the fourth time. Multiples of 4 toggled. So on and so forth. Voltage fluctuated 100 times. Voltage fluctuated 100 times. When the voltage will fluctuate for 51st time, only the 51st bulb will toggle. When the voltage will fluctuate for 24th time, multiples of 24 will toggle. That is 24, 48, 72 and 96 will toggle. Is that clear? Clear or not clear? So let me repeat the question. So far. Listen to the story carefully so far. How many bulbs are there? First point. How many bulbs are there? 100 bulbs are there. Second, all of them are on initially. All are on initially. Okay. Third one. Now the voltage is going to fluctuate how many times? Voltage fluctuated 100 times. Fluctuated 100 times. For the first fluctuation, all multiples of 1, which means all the bulbs toggled. First fluctuation, multiples of 1 toggled, which means all the bulbs. Multiples of 1 toggled. For second fluctuation, all the even bulbs toggled. If they were off, they turned on. If they were on, they turned off. Even bulbs toggled. So on and so forth. I think now it is clear. For third fluctuation, bulb number 3, 6, 9, 12, 15, etc. They toggled. Multiples of 3 toggled. And voltage fluctuated 100 times. For the 100th fluctuation, only the 100th bulb toggled. Now you have to tell me which all bulbs. What is toggle? Toggle means if a bulb is on, it switches off. If the bulb is off, it switches on. Pradeep, is that clear? What is toggling? Toggling means this operation, not of x. So not of x is for true it becomes false, for false it becomes true. Whatever is the state, it reverses. Alright. The fluctuation has toggled 100 times. That is an important part. There were 100 bulbs and fluctuation has toggled 100 times. And in any given fluctuation, for example, it is 40th fluctuation. So 40th bulb and 80th bulb toggles. My question to you. After the fluctuation has toggled for 100 times, after the voltage has fluctuated for 100 times, which all bulbs stay on? Is the question clear? Which all bulbs stay on? Tanmay, this is the first question. Don't worry. So let us. Subrato, Don't write it. Don't write it. So tell me, which all bulbs do you think stay on, and why? And why? Then, Subrat, actually it is correct, but I would request you to delete the comment if possible. No worries. Now you've done it. No worries. Which all bulbs stay on? Bulb number which all? Which all bulbs stay on? And why? My first question to all of you, is the question clear? Is the question clear? Let me know if the question is not clear. If the question is not clear, I would want to repeat the question. So the question is clear. Okay. Pinaki has said the question is not clear, maybe. Okay. No worries, Surat. Now no worries. Already people have written comments. It is gone. Revan's answer is correct. So all the perfect squares, Surat answer was also correct. 1, 4, 9, 16, 25, 36. So these all bulbs stay on. Square numbers, perfect squares stay on. 1, 4, 9, 16, 25, 36, 49, 64, 81 and 100. Reason. Let us think of the reason. Let us think of the reason. Okay. So let me pick any number. Let me pick any number. Let us pick a number like 24. Help me do the factorization of 24. So do you agree 1 into 24 is equal to 24? I hope easy. So let me write all the factors of 24. 24 comes in the table of 1. 24 also comes in the table of 2. In the table of 3. In the table of 4. Then in the table of 6. In the table of 8. In the table of 12. And finally in the table of 24. Is this correct to write? That yes, this is true. 1 into 24 is 24, 2 into 12 is 24, 3 into 8 is 24, 4 into 6 is 24, 6 into 4 is 24, 8 into 3 is 24, 12 into 2 is 24, and 24 into 1 is 24. I hope everyone agrees to that. So, let us say there are, so what I am saying is, after the midpoint, not the midpoint, after the square root, so square root of 24 is somewhere near 5. Do you agree? Arush, I would repeat, no problem. So what I am doing is I have just done the prime factorization of 24. I want to speak about the 24th bulb basically. So I have done not the prime factorization, I have done the factorization of 24. So here is the factorization of 24. 1 into 24 is 24. 2 12 is 24. 3 8 is 24. 4 6 is 24. Okay. Similarly, 6 4 is also 24. 6 4 is 24. 8 3 is 24. 12 2s are 24, 24 1s are 24. Okay. Why bulb number 24? To help you understand something. So wait. So for 24, let me know what do you think is the square root of 24? Somewhere around 5. For 25 it is 5. So 24 square root would be somewhere around 4.999 something. 4.99 something. Correct? So what I am saying is, can you make this observation that after the square root, it is just a mirror image. 4 into 6 became 6 into 4. 3 into 8 became 8 into 3. 2 into 12 became 12 into 2. 1 into 24 became 24 into 1. I would explain why perfect squares. I am going towards that. First understand for 24, then you would understand it. But do you see this? That after the perfect square, it is a mirror image. It is a mirror image. Can you see this? That yes, after the mirror image, after the perfect square, after the square root basically, it is becoming a mirror image. So let me say there are n factors of 24 before the n factors of 24 before the square root and n after that. Can I say for 24 we have 2n factors? Is this becoming clear? That for 24 we have 2n factors. N factors before the square root and n factors after the square root, because all the factors that were there before the square root, for example 4 into 6, only reversed as 6 into 4 after the square root. 3 into 8 became 8 into 3. 2 into 12 became 12 into 2. 1 into 24 became 24 into 1. So what I am saying is, for a number like 24, and I would define what is a number like 24. For a number like 24, the total number of factors are even. So what I have just identified is a number like 24. What do I mean by a number like 24? I would come to that. A number like 24 has 2n, that is even number of factors. Even number of factors. Now let me analyze 36 for you. 36 for you. 36 is different from 24. Then I would ask you, what do you think is the difference between 24 and 36? Let me analyze 36 for you. Let's analyze it together. 1 into 36 is 36. Tell me the next factor. I think easy. 2 into 18 is 36. You have to make a observation here. 3 into 12 is 36. 4 into 9 is 36. What is the next one? What after 4 into 9? What is the next factor of 36? After 4 into 9, I am waiting for you. I am waiting for you. What is the next factor? 6 into 6 is 36. Correct? 36. And after 6 into 6, what is the next factor? What do you think would be the next factor? After 6 into 6, what is the next factor? Not 12. 9 into 4. 9 into 4. This behavior that after the square root, it is just a mirror image of the older factors. 1 into 36 would become 36 into 1. Okay? So what I am saying is, let us say these are n. These are n. So after the square root also there are n. And in the middle stands the square root. So n plus 1 plus n. What I am saying is, a number like 36 has 2n plus 1. That is odd number of factors. Odd number of factors. Okay? So I want you to pay this fact attention. 24 had 2n factors. 36 has 2n plus 1 factors. Okay, I would repeat it, no problems. I would repeat it. Don't worry, this is just a question. I would do it for the next question. So you people can participate in the discussion on the next question. Because if I would repeat it, it would be a waste of time for all the people who joined in time. So don't worry, it is just a question. For the next question, you can come with me for the next question. Let the first question go. A recorded lecture would be available. I would ask the support team to provide you the recorded lecture. But for now, I want your attention and pay this close attention that 24 had 2n factors, 36 had 2n plus 1 factors, and understand what is happening. See what happened. For 24, 1 into 24, 2 into 12, 3 into 8, 4 into 6, somewhere the square root was 4.9 something, which is not an integer basically. And after the square root, it was a mirror image. So 6 into 4, 8 into 3, 12 into 2, 24 into 1. If these are n, so these are also n. So 2n factors, that is 24 has even number of factors. 24 has even number of factors. 36 had 1 into 36, 2 into 18, 3 into 12, 4 into 9. Then we had 4, 6 into 6. And after that it was a mirror image. 9 into 4, 12 into 3, 2 into 18 became 18 into 2, 1 into 36 became 36 into 1. So the total number of factors were n plus 1 plus n, that is 2n plus 1. 36 has 2n plus 1 factors. 24 has 2n factors. Okay. Now think of the 24th bulb. 24th bulb. You have to think of the 24th bulb. 24th bulb. How many fluctuations will touch it? How many fluctuations will be touched? My question to you. Initially it is on. The 24th bulb was initially on. My question. Will the first fluctuation toggle the 24th bulb? My question to you. Will the first fluctuation toggle the 24th bulb? Simple question. Toggle? Yes. So it was on, it would become off. This was on, it would become off. Now, second fluctuation, because 2 into 12 is also 24. In second fluctuation, will we again toggle it? Yes, it will turn on. Will third fluctuation also toggle it? Yes. Will fourth fluctuation also toggle it? Yes. Will sixth fluctuation, after fourth, fifth won't touch it, sixth fluctuation, will also that toggle it? Yes. Eighth fluctuation, 12th fluctuation, and 24th fluctuation. Is this clear? Okay, so initially this was actually off. My question would have been that initially this is off. This was off, turned on here, turned off here, turned on here, turned off, turned on, off, on, off. So what I am saying is, because 24 has even number of factors, it had how many factors? 1, 2, 3, 4, 5, 6, 7, 8. It had 8 factors, or 2n factors, or even factors. It had even factors. So if it was off, it would stay off. Is this clear? A bulb which has even number of factors will stay off. Whatever it was initially, it will stay that way. Please let me know that this fact is clear to you. A bulb like 24, which has even number of factors, 8 factors, 2n factors, even number of factors. If it has even number of factors, it will stay off. From off to on, off to on to off, on, off, on, off, on, off. So if it was off initially, it would stay off eventually. Now for a bulb like 36, if it was off initially, it would become on. Why? Because it has 2n plus 1 factors. 2n plus 1 factors. So 1 into 36, the first fluctuation turned it on. The second fluctuation turned it off. The third fluctuation turned it on. The fourth fluctuation turned it off. The sixth fluctuation turned it on. 9 into 4, ninth fluctuation turned it off. 12th fluctuation turned it on. 18th fluctuation turned it off. 36th fluctuation turned it on again. Why did that happen? Because see this line, n factors here, n factors here, and one more factor. So it has 2n plus 1 factors. It has basically 9 factors. So because it has odd number of factors, that is why if it was off initially, it would turn on initially. Now the question boils down to this: out of the 100 bulbs, from 1, 2, 3, so on and so forth, out of the 100 bulbs, which all has odd number of factors? Sir, on one has to off according to the question. Anush, I changed the question actually. So I made a mistake initially. That mistake was all are on initially. No, all are off initially. So that was a mistake. No problem. Okay. So the question is, which all number has odd number of factors? All the perfect squares. All perfect squares. Which has perfect squares has integral square roots. All perfect squares have odd number of factors. They have odd number of factors. Why? Because they have integral square roots, and the factors are just a mirror image before and after the square root. So if n factors are before the square root and n are after the square root, and square root is integral, it means you have 2n plus 1 factors. For non-perfect square, the square root is not integral, so there are only 2n factors. Okay, so that is why all the perfect square, that is bulb like 1, 4, 9, 16, 24, 5, 36, 49 and 64, 81 and 100. All these bulbs will stay on. These bulbs will eventually be on. Is the question clear to you? Could you understand the question? Do you see that this was a maths question largely? This was not. Once again, the last part. No problem. So, no problem. Let me do a very bad way of explaining it. Let me do it the rough way of explaining it. Take a look. So I would explain for only 25 bulbs now. 25 fluctuations. Okay? Listen carefully. I'll change the question. The question was 100 bulbs, 100 fluctuations. I am doing a smaller question, 25 bulb, 25 fluctuations, so that you can understand. Now pay dear attention. Do not be distracted. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. For the first fluctuation, now tell me, for the first fluctuation, which all bulbs will be touched? The first fluctuation will touch all the bulbs. Do you agree? The first fluctuation will touch all the bulbs. Do you all agree? Yes, because 1 divides all the numbers. That is why the first fluctuation will touch all the numbers. Okay? Second fluctuation. Revant, don't make me repeat the question now. So this is the question. Please listen to it carefully if you have not listened to it. There are 25 bulbs. All are off. Voltage fluctuated 25 times. 25 voltage fluctuations. For the first fluctuation, what is happening? The first fluctuation toggled all the buttons. Second fluctuation toggled all the even buttons. Third fluctuation toggled all the buttons which are multiple of 3. Okay. Sayam, I would just ask the support. They would provide you with the recordings. Let us focus on the class now. Third fluctuation toggled all the bulbs which are multiples of 3. And so on and so forth. There were 25 fluctuations. The question is, yes, first fluctuation toggles all of them. Yes, toggles, so means if they were off, they turn them on. Yes, the first fluctuation will make them, all of them on. Okay. Now you have to tell me now this is the question that I am asking you. These are 25 bulbs. I am going to do the first fluctuation for all of you. You have to tell me the first fluctuation will touch which all buttons. It is very easy. Only you have to be attentive. So is this okay if I say first fluctuation will touch all these buttons? Touch means toggle all these buttons. They were all off. All of them will turn on. All the 25 bulbs will be touched by the first fluctuation. This is the effect of first fluctuation. Are you aligned with me? Yet, yes, the first fluctuation will do this. Now the second fluctuation. You have to tell me, will the second fluctuation touch this button or not? That would help me understand if you are with me or not. Will the second fluctuation touch this button or not? No, because second fluctuation will touch all the even ones. That is this 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now say with me, the second fluctuation will touch all those buttons which can be, all those bulbs which can be divided by 2, of which 2 is a factor. Okay. Now third fluctuation. If you are with me, third fluctuation, it will touch which all bulbs? Will it touch the first bulb? Third fluctuation. Will it touch the first bulb? No. Second bulb? No. Third bulb? Yes. It will touch 3, 6. The table of 3. Multiples of 3 basically. So it will touch 3, 6, 9, 12, 15, 18, 21, 24. Fourth fluctuation. Now quickly, fourth fluctuation. Fourth bulb, 8th bulb, 12th bulb, 16th bulb, 20th bulb and 24th bulb. Fifth fluctuation. 5th bulb, 10th bulb, 15th bulb, 20th bulb, 25th bulb. 6th, 6, 12, 18, 24. 7th, 7, 14, 21. 8th, 8, 16, 24. 9th, 9, 18. 10th, 10, 20. 11, 11, 22. For 12th fluctuation, 12 and 24. For 13th, only 13. 13th twice is 26, nothing. So for 14th fluctuation, only 14th. For 15th, only 15th. 16th, only 16th. 17th, 18th, 19th, 20th, 21st, 22nd. For 23rd fluctuation, only 23rd bulb will be touched. For 24th fluctuation, only 24th bulb will be touched. For 25th fluctuation, only 25 bulb will be touched. Now I want you to analyze 2 bulbs. You have to tell me, will 12th bulb be turned on or off? Take a look how many times it has been toggled. 1, 2, 3, 4, 5, 6. It has been toggled 6 times. So if it has been toggled 6 times, that is even number of times. So let me toggle something 6 number of times. 12th bulb. Toggle it was initially off. Toggle it 6 times. First time became on, second time became off, third time became on, fourth time became off, fifth time became on, sixth time became off. If it was off, it stays off because touched even number of times. For 12, that is what happened. Now take a look at 16. Take a look at 16. How many times it has been toggled? Here you can take a look. 1, 2, 3, 4, 5. 16 has been toggled even number of times. Oh, sorry, odd number of times. 5 times. It turned on, then it turned off. Third time it turned on, fourth time it turned off. Fifth time it turned on. Is it clear to you that if anything, if 12 stayed off because it was toggled even number of times? Even number means off to off. 16 was toggled odd number of times, so on to off to on. Is this clear that why is 12 off and why is 16 on? Perfectly clear. Great. Now let's focus on what happened with 12 and what happened with 16. Now we have to think when all 12 was touched. 10 was touched in first fluctuation, in second fluctuation because it can be divided by 2, in third fluctuation, in fourth fluctuation, in sixth fluctuation, and in 12th fluctuation. The square root of 12 is around 3 point something. So it has, because it has even number of factors. The square root is not integral. The square root is not integral. It is 3 point something something, not integral. So that is why n before the square root and n after the square root. So 2n factors. 2n factors means even number of factors, means it would stay off. For 16, it is a perfect square. Perfect square means it has a integral square root. Was touched in first fluctuation, second fluctuation, fourth fluctuation. After that, just so 2n plus 1 number of factors, which means odd number of factors, which means off to on. Is this question clear or not clear? There are so many no's. Is this clear or not clear? This no is only from one person. No problem. Is this clear to the rest of you? Okay. All right. So largely the question is, can you know what has even number of factors? But you had to actually find it out yourself. Now let me give you a similar question again. So see, from where I see it, this is a mathematics question coming from a programmer. This is what a mathematics question looks like when it comes from a programmer. It is programming also and it is maths also. Okay. I have planned 6-7 such questions. Let me take you through one more such question. Now it would be a permutations, combinations question. Can't we do it in a shortcut way? Of course you can, but you need to figure it out. Of course you can. You actually had to figure it out that it has even number of factors. So this was for discussion, for making people understand. I think if anybody would be doing it, they would be doing it in like 20 seconds. For 500 bulbs, how would you do it for 500 bulbs? So all the square roots, so all the perfect squares till 500, beta. Sakshi is asked, for 500 bulbs, how would you give the answer? No problem. So see, 1 square is 1, 2 square is 4, 3 square is 9. So these bulbs stay on. 4 is 16, 5 is 25, for 6 is 36, 7 is 49. So all these bulbs stay on. So just the squares, 64. For 8, for 9 it is 81, for 10 it is 100, for 11 it is 121, for 12 it is 144. I do not know too many of them. I know till 14. 15 also I know, 225. 16 also I know. 17 also I know, I'm smart. 18 also I know. 19, oh my god, no, 361. 20, 400. I think now I am at my limits. 441, I think, and I'm not sure of that. 464 or 484, not sure again. I think 484. 22 to the 44, 22 to the 44, 484, yes. 23 I think is beyond. So for till 500, these are the numbers. Till the squares go beyond 500. Okay, no problem. What if they toggle by odd number, like 27? This question is not clear. What if they toggled by odd number, like 27? Anush, the question is not clear. Toggled by odd number. Oh, I don't know. Okay, all right. Anuj, when they are toggled 27 times? They will stay on in that case. 27 is, see, 27 is an odd number. 27 means it will stay on. See, 10 stays off, 11 stays on, 12 stays off, 13 stays on. Basically, every odd number of toggles make it on, every even number of toggles make it off. As simple as that. Okay, Anuj, 27 toggles will make it on. Okay, I want to move to the next question. Are you guys ready to move on to the next question? Yes, Kunal, I'll share the notes. I'll attach it to the recording. So the person who will share the recording will also share the notes with you. No worry. Okay, okay, great. So don't look for easy questions. They would be programming questions looking like math questions. So let me throw another one which I have chosen for this particular class. Very interesting question. So this is a pair of two questions. Both the questions are very similar. Okay. So let's see if you would be able to tell me that. Very easy question. Easy if you think methodically. Otherwise, I think hard enough. So you are aware of what binary is? You are aware of binary, no? Yes, you can expect similar questions. So I have picked it from the previous session that was given on maths. Everyone is aware of binary. It only has zeros and ones. Okay. So what is the count of binary strings? So I will incrementally ask the question. What is the count of binary strings? Count of binary strings. How many binary strings are possible? Basically, what the question is, how many binary strings of length? How many binary strings? And I'm going to change the question. So first I'm going to ask the question, then I'm going to change it. How many binary strings of length 5 are possible? How many distinct binary strings of length 5 are possible? Easy question actually. How many binary strings of length 5 are possible? It's a pretty easy question actually. It's a permutation combination question. I expect you to give the answer. I already have the answer. 2 to the power 5. Yes, of course. 32. Of course 32. So why? Because there are 5 spots. Every spot can have 0 or 1. 0 or 1. So 2 into 2 into 2 into 2 into 2. That is 32. Was this much easy for everyone? That yes, for length 5, we can have 32 binary strings. Is this clear to you or not? Okay, let me change the question. So this was the basic question. I just wanted to know that whether you are aware of the concept or not. So it proves you are aware of the concept. Now my question. And I would wait for the answer. How many binary strings of length 5 are possible? Of length 5 are possible if consecutive zeros are not allowed. So zeros can come, but 2 zeros together cannot come. So this kind of binary string can't be the answer. This kind of binary string can't be the answer. They are not allowed because there are consecutive zeros. If consecutive zeros are not allowed, how many binary strings are possible? I need to go to the washroom and use the washroom. I will come back in 2 minutes. Please start solving the question now. How many binary strings of length 5 are possible if consecutive zeros are not allowed? Over to you. Over to you. I will discuss the solution after coming back. Thank you. So I have different kind of answers, 8, 12, 144. Okay. The answer could be 8 actually. Answer could be 8. 8 or 13 is going to be the answer. No, I am not making the NSET paper. I am the person who is reverse engineering the NSET paper. So I know somebody has set the NSET paper, and I am supposed to help you guys prepare for the NSET paper by imagining how he must have set the NSET paper. Okay, so I am reverse engineering it. No problem. Come back to me. So I'm just trying to think how he would be thinking. So he is a programmer with a mathematical background. So he would be combining both the worlds. All right, all right. So see, 13 might be the answer. 8 or 13 is going to be the answer actually. Who has said that? So from where I think most likely Kshitij is the name of the guy who might be setting it. I'm not sure. And I don't even know whether I'm supposed to tell you that or not. I should not do guesswork here. Let's come back to this question. Let me focus on this. Okay. 0 and 1. Okay. So I am changing the question slightly for us. I am changing the question like what? So let us say I am solving the same question. But I am solving it like this. What if there's one additional rule? How many binary strings of length 5? I'll go to length 5 of. So what I started solving was instead this. How many binary strings with no consecutive zeros of length n instead of 5 of length any given length a function length n are possible, and I solved this twice. If the string ends with a 0, if the string ends with a 1. So see, any binary string would either end in a 0 or end in a 1. Do you agree that yes, any binary string, either it will end in a 0 or in a 1? Because it is a binary string, has to end with a 0 or a 1. Okay. So see what I am solving. If I solve this question, will we have our answer? How many binary strings with no consecutive zeros? That is what our question was. Binary strings with no consecutive zeros of length n instead of 5. I am solving for any generic n. If I get a function, I would put the value of n equal to 5 and I would get my answer. Are possible if the strings end with a 0, if the strings end with a 1. So whatever is the answer of these two, if I add that up, Bharat, I do not have the access to previous year's question. Let us focus on the question now. If I add the two answers, would not I get the answer? If I add the two results that I get for these two, would not I get my answer? So I've changed the question. The question was, how many binary strings of length 5 are possible if consecutive zeros are not allowed? Good. Okay. So I just changed it to, can I say, relevant binary strings of length 5 ending in 0 plus relevant binary strings of length 5 ending in 1. Let me repeat the question. See, question is, how many binary strings of length 5 are possible if consecutive zeros are not allowed? This is what the question was. Okay. Now, how am I going to solve it? If I solve this thing, you guys understand functions, no? I hope you understand f of x equal to x square plus 3x plus 2. You guys understand, no? That. And if I say put value of x equal to 5, so I hope everyone knows f of 5 equal to 5 square plus 3 into 5 plus 2. Everyone knows that? Okay. So what I am trying to do is define this problem in terms of a function. So let us say there is a function f. With two variables, x comma b. B is binary. X comma b. B is binary. B can be either 0 or 1. Alright. So what I am saying, if I solve this part, f of n comma 0, and this represents what? This represents, please listen carefully what I am saying, count of binary strings. It represents count of binary strings of length n with no consecutive zeros. With no consecutive zeros. That is the meaning of this function. No consecutive zeros. And ending in 0. And ending in 0. This is what my function represents. This is what my function represents. You just have to. So this is like that algebra part where we say, let us say x is Ram's father's age. That kind of thing. Let us say this function of n comma 0 represents count of binary strings of length n with no consecutive zeros and ending in a 0. Okay. Let us say f of n comma 1. Let us say. So let us say is important part here. Let us say is important part. Let us say f of n comma 1 represents what? This function represents count of binary strings. It represents what? It represents the count of what? Of binary strings. Okay. Of which length? Of length n. Is there any rule? Yes, there is a rule with no consecutive zeros. With no consecutive zeros. And ending in 1. Can I say my answer would be f of n comma 0. So you have to tell me what would this give. Would this give me the answer for? Would this give me count of binary strings? Count of binary strings of length n. With no consecutive zeros. This would give me that. And what was my original question? My original question was how many binary strings with no consecutive zeros of length 5 are possible. So if I have this function, all I have to do is I have to do f5 comma 0 plus f5 comma 1. So I'll get the answer. So my problem has changed to defining this function. If I define this function, I am sorted. Okay. So let me use something called recursion in programmatic terms. And if you would want to speak in mathematical terms, I will say principle of mathematical induction. I'll use induction. Kind of. Okay. So let us solve it for n equal to 1. If n was 1. So on this axis I have n. If n was 1. So help me define f of n comma 0 and f of n comma 1. For one length string, please stay with me and pay as much attention as you can because it is getting hard. It is getting difficult. My question, for length 1, how many binary strings of length 1 are possible which end in a 0? Let me again say my question. It is a very simple line that I am saying. How many binary strings of length 1 are possible which end in a 0? 1. And what is that binary string? That binary string is actually only 0. My question to you, how many binary strings of length 1 are possible which end in a 1? How many binary strings of length 1 are possible which end in a 1? 2. Length 1. Of length 1, there are only 2 binary strings. No, if length is equal to 1, only 2 binary strings are there. Which are they? 0 or 1. So how many of them end in a 0? 1. One of them ends in a 0, that is only 0. How many of them end in a 1? 1, that is 1. Is this clear or not clear? Is this first part clear or not clear? Shubham, please do not do that. Do not write 2. Please. Okay, cool. Now I would use principle of mathematical induction and try to solve for n equal to 2. Okay. So from n equal to 1, how can I reach n equal to 2? See, I want to solve for binary strings that end in a 0. Any binary string of length 1. So let us say this is a binary string of length n minus 1. Please pay this attention. This is a binary string of length n minus 1. How can I make it a binary string of length n? By either appending a 0 or by appending a 1. Do you guys agree that yes, any binary string of length n minus 1, if you would append a 0, it would become a binary string of length n ending in a 0. a binary string of length n ending in a 1. Does this last part make sense? That I had a binary string of length n minus 1. If I append a 0 to its end, I would get a binary string ending in 0 of length n. If I append 1 to it, I will get a binary string of length n ending in 1. Do you guys agree? This simple part, this simple picture, very simple picture basically. Again, yes, I will say it again. Okay. See. I had a binary string of length n minus 1. This is a binary string of length n minus 1. Now my question to you, if I append a 0 to it, what do I get? If a binary string of length n minus 1 is appended with a 0, do I get a binary string of length n which ends in a 0? Can I say that? And if I append 1 to it, do I get a binary string of length n ending in a 1? As simple as that. Okay, cool. But you also have to remember, why is there a no here? I don't understand the no actually. So you have to just understand this simple line that I am saying, which is very easy. I can say it again, and please say no again if you do not understand that simple line. All I am saying is a very simple line I am saying. Let me say I gave you a binary string of length n minus 1. If I append a 0 to it, do I get a binary string of length n ending in a 0? How can that be a difficult line to understand? If this binary string of length n minus 1, I append a 1 to it, do I get a binary string of length n ending in a 1? Correct. So see, now I want binary string of length 2. Okay. So what I would do, when I have to make binary string of length 2 ending in a 1, what I would do is append 1 at the end of this and append 1 at the end of this. 0, 1, 1, 1. The count would be 1 plus 1, 2. Easy. So I picked all the binary strings of previous level, and appended a 1 at the end of them. 0 became 0, 1 and 1 became 1, 1. Easy peasy. How could that be hard? Which is the same thing that I said previously. That two binary strings of length n minus 1, if you append a 1, you get binary string of length 2 ending in a 1, 0, 1, 1, 1. 1 at the end of this 0 and 1 at the end of this 1. So I got 0, 1 and 1, 1. So the total count is 2. Easy peasy. Similarly, if I am supposed to get binary string of length 2 ending in a 0, at the end of them I would append zeros. So this would become 0, 0 and 1, 0. That would give me a count of 2 here also. But my question to you, are consecutive zeros allowed? Are consecutive zeros allowed? Consecutive zeros are not allowed. So when you would append 1, pick any, see carefully now. Pick any binary string of n minus 1. Any. Whether it ends in a 0, whether it ends in a 1, does not matter. You append 1 to it, you get a binary string of length n ending in a 1. But when you pick a binary string of any length n minus 1 and append a 0 to it, you get a binary string of length n ending in a 0. That is true. But there is one more rule. You do not have to have consecutive zeros. So while making binary string of length n ending in a 0 with no consecutive zeros, you have to make sure that the binary string that you picked of length n minus 1 did not end in a 0. This was a long line that I have said. I would again say it. See, listen to it carefully. See, now see carefully. This is good. This is the binary string of length n minus 1 ending in a 0. This is the binary string of length n minus 1 ending in a 1. Now my problem is make binary string of length n ending in a 1. No problem. To these binary strings also you can append a 1, and to these binary strings also you can append a 1. You would get a binary string of length n ending in a 1 with no consecutive zeros. But when you are making binary string of length n ending in a 0 with no consecutive zeros, you can append a 0 to this one, but you can't append a 0 to that one. Why? Because if you append a 0 to that, it would become 2 consecutive zeros. So binary strings of length n ending in a 0 is actually equivalent to binary strings of length n minus 1 ending in a 1. Hard to think, but not that hard. Actually, if you come back to picture, you would understand it. See, to this 0 you can't append a 0. To this 1 you can append a 0. So basically this 0 0 is incorrect. When I would make that value, I can only append a 0 to this. So my count would be 1 only. Okay. So I would redo it many times. Don't worry. I would redo it 3-4 times so that you can understand it. I generally redo it and that helps people understand. Now see, for length 3, please stay with me and do for length 3. If you are understanding it, you would be able to understand it. For length 3 and ending in 1. Ending in 1 means they would contribute and they would contribute. You would get 3. How? To 1 0 append a 1. To 0 1 append a 1. To 1 1 append a 1. No problem. But here you would get 2 only. Because you can append a 0 to these. You can't append a 0 to that one. Because that would make 1 0 0, which is not allowed. But you can append a 0 to this. 0 1 0, 1 1 0. We can use gap method to solve this. This is actually the gap method only. This is gap method in programmatic terms. I call it inclusion exclusion basically. Okay. For length 4, to find binary strings which end in length, which end in 1, the answer is 5. You can append a 1 to either of them. 0 1 0 1, 1 1 0 1, to these 3 also, 1 0 1 1, 0 1 1 1, 4 times 1. But ending in 0, you would get only 3 because you can't append a 0 to these, but you can append a 0 to these. So 1 0 1 0, 0 1 1 0, 1 1 1. See, this is fairly easy actually. This is a pragmatic way. There could be other ways, but this is the one that I am aware of. For length 5, what I would say is 8 of them end in a 1 and 5 of them end in a 0. For 0, you can have only this set. Only this set. You can append a 0 to these. 0 1 0 1 0, 1 1 0 1 0, 1 0 1 1 0, 0 1 1 0, 4 times 1 0. But for this one, you can append a 1 to these as well as these. So 1 0 1 0 1, 0 1 1 0 1, 1 1 1 0 1, 0 1 0 1 1, 1 1 0 1 1, 1 0 1 1 1, 0 4 times 1 and 5 times 1. So this is the set of strings, 13 strings. Not understood, I would explain it again. So people are saying, is there an easy way of doing it? Of course, there might be easier ways of doing it. But what if I ask you the strings? What if I ask you the strings? So then it will become difficult also. Okay. Can you please easily didn't understand a single thing? Yes, Mayank, I would redo it. No problem. No problem. I would redo it. But this is the easiest way that I am aware of. I'm sorry, but this is the easiest way that I am aware of. Let me redo it for you so that you can understand it. But this is actually, Anuj, even if n is 100, this is solvable because this would eventually become a formula. So this formula would become f of n equal to, if you would paying attention, so this would become f of, so this is becoming a formula. This is actually the Fibonacci, if you would see, 1 1 1 2, 2 3 3 5, 5 8. So this is basically Fibonacci. Okay. Basically adding the previous two terms. So this is equal to, it starts from a equal to 1, b equal to 1, and then c is equal to a plus b. And then this repeats over and over again. This is basically Fibonacci. Let me redo it again. Where when we practice this type of questions. This is mathematical aptitude generally. Okay. So my few questions to you before I redo this question. I'm going to redo this discussion. And redoing the discussion is going to help you a lot. But before I redo that, what I want to ask is, did you guys understand what I told here? What I taught here? How are we supposed to do this in 2 hours of time? So what I am saying is this is actually mathematical aptitude. This is not that hard. This is not that hard. This is binary mathematics at play. You did not understand it. No, I will do it. I will redo it. Don't worry. So now you have to listen to the question carefully. If you listen to the question carefully, you will be able to do it. Okay. So see what I am doing. So Revant, the formula, there is no formula. This is a function. So this is a function. So if you would ask me to define the function, of course there is a function. F of n is equal to f of n, or I will say g of n ending in 0 plus g of n ending in 1. And if you would ask me to define these, easy to define. G of n comma 0 is equal to g of n minus 1 comma 1. This is a recursive function if you think. And g of n comma 1 is g of n minus 1 comma 1 plus g of n minus 1 comma 0. So the mathematical expression of what I have just taught is this. See, now come back. F of n is the number of binary strings of length n with no consecutive zeros. Let me again say, f of n is the number of binary strings of length n with no consecutive zeros. Okay. So what is g of n comma 0? The number of binary strings of length n ending in a 0 with no consecutive zeros. What is g of n comma 1? The number of binary strings of length n ending in 1 with no consecutive zeros. Okay. And then I have expressed it recursively. So this goes on and on. So Meshwar, I cannot move forward because there are plenty people who did not understand it. And I understand their quandary. It is actually difficult if you are learning this for the first time. Okay. Now come back and try to do it with me. Any generalized method to solve this so we don't have to make the table every time and save time. So Vardhan, the generalized way of finding this is you do the table for 2-3 steps and identify this function. Basically, why is the table required over there is because it is a recursive function. Function expressed in terms of itself. Function expressed in terms of itself is a recursive function. So that is why there is a problem. So the function is calling itself every time. Yes. For a smaller value. That is what is happening. So we tried to know how much is the count for 5. For that, you have done such questions. Let me tell you. Have you done factorial or not? In your life, have you done factorial or not? Have you done factorial or not? You have done factorial. So how do you define 5 factorial? There are 2 ways of defining it. One is 5 into 4 into 3 into 2 into 1. There's another way of defining 5 factorial. What is that? 5 into what? How do you define? 5 into what? 5 into what? My question to you. There's another way of defining 5 factorial. No, 5 into what? 4 factorial. 4 factorial. Which means it is a recursive function. So if I have to define factorial in terms of f of x, can I say that f of x is equal to x into f of x minus 1? This is how you define a factorial. If x is greater than 0 and is equal to 1 if x is equal to 0. That is how you define factorial. So similarly, this function of mine that I just wrote would be defined like this. And if n is 0, then I would define g of n comma 0 is 1, g of n comma 1 is 1. So all in all, this was a question of function forming. This was a question of defining a function. So eventually, if I would define it only in mathematical terms, I would end up with this. F of n is equal to g of n comma 0 plus g of n comma 1. And g of n comma 0 is g of n minus 1 comma 1 if n is greater than 0 and equal to 1 if n is equal to 0. And g of n comma 1 is g of n minus 1 comma 1 plus g of n minus 1 comma 0 if n is greater than 0 equal to 1 if n is equal to 0. So this is the mathematical expression of previous question. Okay. Can we do any math topic from JEE preparation module? I don't think so. I think the ones that I could not mention. So initially I told you these sections. So which sections? Probability and statistics. You just do +1, +2 stuff. That would be enough. Ratio and proportion, 10th stuff is enough. Sets, 10th stuff is enough. But for this stuff like permutation and combination, this kind of information might be required. Now, the questions are not going to be simply apply the formula and answer. Of course not. That is what I am talking. So this maths, you call it applied maths if you want to. The questions are not going to be apply a formula and get to an answer. The question is going to think and reach an answer. Okay. Do you want me to redo the question? I want to redo the question if you are there. If you want to redo it, I want to redo it again also. Because I think a lot of people might find it hard. Yes? It will be fun, no? It will be fun, na? To redo it again. So even for people who had understood it, they would be able to understand it better. Okay. So what was the question? What was the question? How many strings? How many strings? Okay. How many binary strings? Binary strings means 0 and 1. How many binary strings of length 5 with no consecutive zeros are there? No consecutive zeros are there. Okay. Sakshi, I do not have the previous year questions with me. All right. So let us focus on this question now. How many binary strings of length 5 with no consecutive zeros are there? So let us try to think it step by step. Okay, binary strings of length 5. That is easy. If the question was binary strings of length 5, only this much, it is easy. 5 spots. Every spot can have 0 and 1. So 2 into 2 into 2 into 2 into 2 into 2 into 2 equal to 32. I think this is dumb and everybody can think of it. Everybody can think of it. This is the easiest thing. I think nobody has a problem in thinking of this much. But my question is different. So I started defining it. So I said, would I be able to get my answer for any length n? So f of n represents binary strings, count of binary strings of length n. Can I say, can be defined in terms of this? If f of n comma 0 and f of n comma means length of binary string, number of binary strings of length n ending in a 0, number of binary strings of length n ending in a 1. Easy thing basically. But if you listen to it carefully, then you would be able to make sense of it. Number of binary strings of length n ending in a 0. Number of binary strings of length n ending in a 1. Alright. So if I add the count of those, would I get the number of binary strings of length n? Yes. This function has one more rule. These are not ordinary binary strings. These binary strings do not have consecutive zeros. Okay. Now I would use mathematical induction. Mathematical induction was what? You solve for n equal to 1, then you solve for n equal to k, then you prove for n equal to k plus 1. That is what mathematical induction was. So something of the same sort I would use. So this is induction basically happening. Length 1. Here we have n or length. 1 length, 2 length, 3 length, 4 length, 5 length, 6 length. So on the left hand side, what do I have? Or let me just have n equal to 1, 2, 3, 4, 5. So f of n comma 0. Remember, what does it represent? It represents binary string of length n ending in a 0. Binary string of length n ending in a 1. So what does it represent here? Binary string of length 1 ending in a 0. Yes, Sheikh, of course it can be done the other way around also. Okay, but important part. What does this spot represent? This spot represents number of binary strings of length 1, because n is 1 here, ending in a 0. So now tell me all the binary strings of length 1. So I want to write all the binary strings of length 1. All binary strings of length 1. Tell me what are the binary strings of length 1? How many binary strings of length 1 are there? And what all are they? Only 2. There are 2 of them. Which 2 are there? Only 0 and 1. Length 1. And the total count is 2. Correct? So if I wanted binary strings of length 1 ending in a 0 and ending in a 1, the count is 1 each and the answer is 0 and 1. Length 1. Can you see the length 1 here? Yes, length is 1 and the count is 1 and 1. Okay. Now I was saying this thing. Now take a look at this thing. If I have a binary string of length n minus 1 and I append a 0 at the end of it, do I get a binary string of length n ending in a 0? And if I append a 1 at the end of it, do I get a binary string of length n ending in a 1? Easy thing basically. I think this is easy. Okay. Now I would help you think it in another way also. So here here is a binary string of length n minus 1 ending in 0. Here is a binary string of length n minus 1 ending in 1. Now I want to ask, if I append a 1 to the end of it, and if I append to the end to the 1 of it, what do I get? Can I say I still get a binary string of length n ending in a 1 and with no consecutive zeros? This has no consecutive zeros, this has no consecutive zeros. I have just appended a 1, so I get a binary string of length n ending in a 1 with no consecutive zeros. Can I say, if a binary string of length n minus 1 ending in a 0 is appended with a 1, and binary string of length n minus 1 ending in a 1 is appended with a 1, I get a binary string of length n ending in a 1. Same way, can I say, so I had a binary string of length n minus 1 ending in a 0. A binary string of length n minus 1 ending in a 1. Can I append 0 to both of them to get a binary string of length n? Or there is a problem here. There is a rule of ours that is preventing it. Is there a rule of ours that is preventing it? Which rule is preventing this? Which rule is preventing this? The consecutive 0 rule. This is okay. This part is okay. A binary string of length n minus 1 ending with a 1, if you append that as a 0, fine, you get a binary string of length n ending in a 0 and no rule is violated. But if you append a 0 to this binary string, there are consecutive zeros. That is not allowed. So, binary string of length n ending in a 0 will derive only from binary string of length n minus 1 ending in a 1. Now, if you are with me, what I am saying is this value is equal to sum of these two. And this value is only that value. Okay. So that is not clear. Let me show how that is happening. So to get a binary string ending in 1, you can append a 1 to the end of this and to the end of these. Both of them. 0, 1, 1, 1. So count is 2. But here you can't append a 0 to the end of this. But you can append to the 0 to the end of that. So only this value would be copied. And it would become 1, 0. Similarly, if you have to get this. So length 3 will get its answers from length 2. Because n minus 1 by length, you pick a binary string of length n minus 1 and then you make a binary string of length n by appending a 0 or 1 to the end of it. Okay. So you can append a 1 to the end of all of them basically. So you would get 3, 1 plus 2, 3. You can append a 1 to all of them. 1, 0, 1, 0, 1, 1, 1, 1, 1. But you can append a 0 not to this. But you can append a 0 to these to get binary string of length 3 ending in a 0. 0, 1, 0, 1, 1, 0, the count is 2. For the next spot, here you have 5 because you can append 1 to all of them. Okay. So I would have a, alright. So I think now it is making sense to you. Is this making sense to you? That this is 8. This is 5. Eventual answer is this plus this, 13. Eventual answer is 13. Make sense? Was it difficult? Was it very, very, very difficult? Was it very difficult? Or was it like, okay, this is functions and relations? Actually, we had to figure out the functions and relations. It was a hard question. Nonetheless, it was a hard question. Where can we find these topics and questions? So, this is what you would get in... this is permutation and combination basically. So try to see this question again. What do you think is this question? This thing is basically permutation and combination. No? In which topic will this question come? How many binary strings of length 5 with no consecutive zeros are there? This is a permutation combination question basically. Okay. This is a dynamic programming question also. This is a recursive function problem also. This is a permutation combination problem also. So multiple math chapters basically. Can you solve it for n equal to 100 or something? No problem, Mansha. Why is there not a problem basically? Why is there not a problem? Because I have the recursive function available now. So if you would ask me if can I solve it for that, of course I can. How can I? Because I would eventually realize that this is Fibonacci. This is Fibonacci. 1, 1, 1, 2, 2, 3, 3, 5, 5, 8. Fibonacci. So Fibonacci of n is basically Fibonacci of n minus 1 plus Fibonacci of n minus 2, and this can be solved for n equal to 100 also, no problem. No, and not necessarily recursively. So I would change it into something called a logarithmic function. So for 100, I will only need to do 10 operations. Okay. If we write 8 as answer, then it will, yes, of course, 8 was not an answer. No, 13 was the answer basically. 13 was the answer. So at the end, you would have to add both of them. Where can we practice this kind of problem? Where can we practice this kind of problem? So let me share the screen basically. You would do yourself a favor by practicing from where? So you can go to this, and you can go to this, and you can go to this link, and you can go to dynamic programming and greedy. Okay, there are a few questions here. You don't have to code them. There are 30 questions basically. You don't have to code them. So out of those 30, choose any 15 that you want. And actually, which 15? So the last question that you have to practice is partition into subsets. Don't go any beyond that. Partition into subsets should be the last question that you should practice. And so this makes it 25. And you can skip 12 out of them. So practice any 12, 13 questions from the top 25 questions. Just watch the part before the coding. Just watch the part before the coding. That would help you in learnability also. That would help you in permutation combination part of your maths also. So that is what my advice is. And I think this might work, because a lot of DP questions might, a lot of permutation combination question might be like this. Should we practice one more question on the same concept that I have just taught? I just want to see whether you can do permutation combinations or not. I'm going to use the exact same topic. So see what I'm going to do. I'm going to give you the exact same question, but that question will not look like this at all. What I'm saying, an amazing thing I am saying, exact same question, but it will not look like this at all. Okay, so see, just give me 1 second. So learnability is 65, maths is 65. Learnability 65, and I think logical reasoning is the rest of it. Within maths, I cannot tell you the weightage. I don't know, actually. Just give me 1 second. My pencil is not charged. Is calculator allowed during the exam? You're giving it from home. The exam is proctored, but I don't think calculator is not disallowed. So calculator is okay. Number of questions asked in math, not sure. 65, I think every question is the one question. Share previous lecture note. Don't, let us come back to what we are doing right now. So such an interesting class is going on. You are asking other questions. So I want to ask you a ditto same question, but that question will be slightly different, and let's see whether you would be able to figure out that last part or not. Can you say top? Yes, I can tell you the topics. So the topics are, yes, Bharat, the topics are, the first topic is number theory, where I have advised you to do modular arithmetic. I have shared a article link with you already. No. The second is exponentials and logarithms. My advice here is to be very familiar with binary number system. Third is probability and statistics. I have given no advice on that. Fourth is permutation and combinations. I have just given you a link to practice that. Permutation and combination questions will come with a program, might come with a programming background. Why? Because the person who might be making these questions may be coming from a computer science background, and he may be thinking from dynamic programming perspective. Ratio and proportion, no advice. Do your 10th stuff, 10th, 12th stuff. Property and statistics, 10th, 12th stuff. Sets, no advice. Do your 10th, 12th stuff. For 3 topics, I have given you a specific advice. In number 3, revise modular arithmetic. I have shared the link. Exponential logarithms, do binary system as deeply as possible. Permutation combination, I just shared a link with you. Do 12 questions out of those. Might help. Okay. Yes, I am. Article link. I have pinned the article link. So article links are in the pinned chat. Okay. Now let me do the question if possible. So here is the question. So there is a floor. And you have to tile the floor. Share all the links previous one also. They are in the pinned chat. I hope you can see the pinned chat in the top. So they are in the pinned chat. Both the links are there. Okay. Now let us come back to the question. Here is a floor. You have to tile the floor up. You have to tile up the floor. Okay, the floor's width is 2, the floor's length is n, let us say n is equal to 10. Okay, the dimensions of the tiles are 2 cross 1, 2 cross 1, 2 cross 1. You can either use a tile vertically, or if you want you can use a tile horizontally. In how many different ways can you tile up the floor? This is the exact same question that I've taught you just now, and the question might not at all, board is not visible, sorry. I have taught you the exact same question just a minute ago, and I'm going to ask you the same question. Okay, let's see if you can connect the dots. See, let me again tell you the question. You have to tile up a floor. Tile up a floor. This is the floor. This is the floor. The width of the floor is 2. Okay, screen is visible right now. Can you see the screen now? Yes. The length of the floor is n. Let us say n equal to 10. And a given tile is 2 feet wide. The dimensions are 2 cross 1. And any given tile you can use horizontally or vertically, whichever way you want. Okay, so let me show you a possible way of tiling it up. First tile was used vertically, then 2 tiles were used horizontally. The dimension is 2 cross 1, then vertically, and finally 2 of them are used horizontally. Okay, you have to tell me the number of ways in which this floor can be tiled up. The number of different ways in which this floor can be tiled up. This is very similar to the question that you have just solved. The final function would be similar, but the question does not look the same at all. So you'll have to figure out how the question is same. But is the question clear? Forget about the relation with the old question. Is the question clear? The question is, there is a floor, you have to tile it up. The tiles are there. I have asked, in how many ways can you tile up the floor? Is the question clear? Yes, basically you have to find the number of arrangements of 2 cross 1, horizontally, vertically, whichever way you do it. No, not 144. The answer is Fibonacci. Basically, the answer is Fibonacci. Fibonacci of 10. Most likely the answer is 55. Most likely the answer is 55. There are 55 different ways for 10. So solve it. You can't solve it for n equal to 10. Try to solve it for n equal to 5. For n equal to 5, the answer is most likely 8 or 13. 8 or 13. So can you do it for n equal to 5? So this is one question. No, not 7, beta. The answer is Fibonacci. Fibonacci. So the answer is Fibonacci of 5 is either 8 or 13. So the answer is 8 or 13. It is not 7. Okay. So this is one question. Don't worry about solving this question right now. So the link that I have given to you, there is a question called m into 1 tiling problem in the link that I have shared with you. Told for n equal to 10. For n equal to 10, it is 55, not 144. So go through those links, solve this problem from there, and you would see how it is similar to that. One more question. Let me see whether you would be able to do this. So there is a street. Here's a street. And let us say there are 4 plots. Plot. There are plots on both sides of the street. Here, either you can leave an empty space, or you can build a building, or you can leave a space. You can either leave a space or build a building. Up to you. Space, building, space. Up to you. Okay. The street length is, let us say, 4 plots. 4 plots. 4 plots means 4 plots on that side, 4 plots on this side. Now my question to you. In how many ways can we build buildings in this street? in how many ways can we build buildings in this street if no two adjacent buildings are allowed? Can you see how this is similar to the old question? Fibonacci, no, it's not Fibonacci, it is Fibonacci. It is Fibonacci function. Fibonacci. Fibonacci of 10 is 55. Fibonacci. Fibonacci of 10 is 55. Okay. Is this question clear? The next question that I am throwing to you, is this question clear? There is a street 4 plots long. 4 plots on the left of it, 4 plots on the right of it. Adjacent buildings are not allowed. You can either build a building or keep an empty spot in the plot. So in how many ways can you build the buildings over here? Do you see how it is similar to the 0-1 problem? In 0-1 problems, we can build only on the plot, of course. So there are 4 plots on that side and 4 plots on this side. So what you are allowed to do is, space, building, that is allowed. But what is not allowed is building consecutively is not allowed. The answer is not 14. Answer is how much? Answer is, I think, 60. For 4 length, I think it is 64. For 4, it is 64. For 4 length, answer is 64. So do you see it is the same question actually? The old same question. Forget both sides. Only focus on one side. The values allowed in one box is building or space. 0 or 1. No 2 zeros are allowed. No 2 buildings are allowed. Do you see that it is the same question as the previous question? For one side is the same question. No 2 zeros are allowed. So you can have building space, you can have building space, you can have space building, you can have space building. So for one side, it is the same problem as 0-1 problem. So one side can be done in how many ways? 8 ways. Both sides can be done in 8 ways. So 8 into 8, 64 ways basically. So the old question is, it is the same as the old question. This same question, this same table. For 4 length, we had the 8 answer. So 8 square is the answer here because 8 ways you can do the left side, 8 ways you can do the right side. 8 cross 8, 64. So my question to you, simple question that I want to ask is, could you relate this question to the 0-1 problem? That is what I am interested in. I am not interested in the answer of this. Could you relate it to the 0-1 problem? And could you figure it out that you would have to square the answer of 0-1 problem? Square the answer of 0-1 problem because 8 on that side, 8 on this side, 8 cross 8. So this is what I am talking. So that you now have the basic tools of it. Cool, great. All right. So don't worry. I have 2 more sessions with you. One is learnability, another session, and one more math session. So I would do a mixture of learnability and math in both of them. Don't worry. Okay. So meanwhile, you can practice from the resources that I have given to you. Don't worry about the permutation combination. I would help you cover most of it. So not most of it, but at least you would have some advantage while sitting in the exam because you would know what to expect. Can you download the note PDF that you create now? So wait, let me share the now that if that is possible. Quick share. Airdrop. So I have the PDF. Just give me 1 minute. Let me share the PDF with you. How to share the PDF? I would drop it in a drive and share the link. Okay. So here is a Google Drive. I would upload. I think this is the 8th January, no? Yes. Just give me 1 minute. So let me upload it and share what I can. share, share, anyone with the link, copy link, done. Just give me 1 second and let me know that can you check the notes or not. So please try to open this link, this last link. Can you check this out? Can you open this out? Okay, all right. Drop that in the WhatsApp. There is no WhatsApp group. I am not aware of any WhatsApp group. You guys drop it there, no? Previous lecture notes. All right, don't worry. I have those available also. So let me find previous lecture notes. Yes, I have previous lecture notes also. So sharing those also. Just one more minute. This is basically, mathematical aptitude at the heart of it. This is mathematical aptitude. So here's the second link of the previous lecture. Let me know whether you can open this also or not. If there's a problem, let me know. Okay, all right. So I know that this was hard, but did you enjoy the class? I know it was hard. It was not easy, but did you enjoy? So so this is computer science and maths combined. How maths and computer science together look cool. All right. See you guys day after tomorrow also. All right. So in the next class, I would try to touch upon some recursion more, and some bit manipulation, because I think a few questions will be there on the bit manipulation, especially the part that is written as exponentials and logarithm. That would actually be bit manipulation from where I think. So good night. It was lovely meeting you guys. Bye bye. 4 lectures are there, Sheikh. The 2 are already done. 2 I would do more. I think 4 would at least give you some fighting chance. Good night. Bye bye. Good night. I can do the C's problem, no worries. In the next lecture, I can do the C's problem if you want. Bye.